The first hint that something was wrong with 3I Atlas arrived wrapped in a kind of urgency you don't normally see in astronomy. A researcher claimed to have found a smoking gun in the newly released XRISM observations, an X-ray glow around the interstellar comet that looked less like a melting snowball and more like the steady burn of a spacecraft engine. The comet, according to that initial claim, was glowing in X-ray frequencies with a color balance that didn't match the chemistry of typical cometary gas, shining forward rather than trailing behind, and radiating a smooth, stable light rather than the jittery flicker of natural outgassing. And almost instantly, scientists found themselves confronting a far sharper question. What if 3I Atlas isn't a comet at all, but something unnatural? Speculation is easy to spark, but much harder to sustain. And yet, this was one of those cases where the timing, the data, and the sheer peculiarity of the target made the question linger longer than usual. XRISM, the new generation X-ray imaging and spectroscopy mission, jointly operated by JAXA and NASA, had been watching the comet from November 26 to November 28, 2025, successfully tracking it across the constellation of Virgo with 14 precise attitude adjustments. The observatory's X-10 imager gathered nearly 17 hours of data, producing one of the most detailed X-ray snapshots of an interstellar visitor ever made. The raw images, calibrated to reveal soft X-ray emissions invisible to the human eye, showed an extended glow around the object, faint, diffuse, but unmistakably present, stretching nearly 400,000 kilometers from the comet's nucleus. Under ordinary circumstances, X-ray emission around a comet is not strange. Since the 1990s, astronomers have understood how solar wind ions, high-speed particles streaming from the sun, interact with neutral gases escaping from a comet's surface. When these ions steal electrons from those gases, they emit soft X-rays in a process known as charge exchange. It's a natural phenomenon, almost routine for icy bodies passing through the inner solar system. But 3I Atlas is not a typical comet. It comes from somewhere far beyond the sun's gravitational neighborhood, a relic from another star system entirely. Its chemical makeup, its activity level, and even the structure of its coma are all shaped by environments we've never directly sampled, and that alone makes any anomaly worth a closer look. The XRISM data immediately raised questions. The soft X-ray glow, mapped through false color representation, showed unusually strong contributions from carbon and nitrogen, while oxygen appeared faint or nearly absent. For a comet, this is not impossible, but it is atypical. Most comets release water vapor as they warm, and water breaks into hydrogen and oxygen, producing strong oxygen line emissions during charge exchange. If oxygen is faint, it means several things. The comet may have unusually low water content, the solar wind conditions may have favored other ions, or the mapping may be reflecting subtle detector quirks, but in a narrative sense, dominated by the drama of a newly arrived interstellar voyager. It's hard to ignore that carbon-nitrogen dominance resembles certain controlled plasmas on Earth, most famously those used in specific types of rocket engine test chambers. The similarity is superficial, yet evocative enough to color the early interpretation.
Even more curious was the spatial behavior of the glow. In typical comets, gas streams outwards and forms a halo or tail structure, shaped by the interplay between solar radiation, the comet's rotation, and the solar wind. The bright regions usually appear offset or trailing, indicating how the gas expands and disperses. But the XRISM image suggested that the brightest portion of the glow leaned forward, toward the sun. In a natural scenario, this could indicate the solar wind was sweeping toward the comet from that direction at the time of observation, intensifying charge exchange on the sunward side. Solar wind anisotropies can create lopsided X-ray halos. This has been observed before, but the effect rarely appears as clean or as sharply defined as what XRISM's early images hinted at. Then there was the question of steadiness. Natural outgassing tends to fluctuate. Over hours or days, a comet's jets pulse, fade, restart, or rotate into view. These dynamics often produce uneven or patchy halos in X-ray imaging. The emissions surrounding 3I Atlas, however, looked strikingly stable, smooth, consistent, lacking the chaotic texture normally seen when a comet's activity pattern shifts. Some of this smoothness can be attributed to the integration of long exposures.
XRISM collected data over many hours, effectively averaging temporary fluctuations into a uniform field. But even accounting for that, the appearance retained an unusual clarity, as though the source were continuous rather than episodic. All of these quirks taken together built an atmosphere of mystery around the object, a foreign body from another star arriving with a composition that didn't match our expectations, an extended halo of X-ray emission larger than a planet, a glow skewed in a direction that suggested pressure, interaction, or some form of sustained energy input. The patterns of color, shape, and stability tempting some to draw parallels to engineered systems rather than frozen geology. And yet, every one of these observations has a plausible natural explanation. Carbon-heavy chemistry might simply mean the comet formed in a region rich in carbonaceous compounds, a feature not uncommon in dense molecular clouds. Solar wind direction and intensity often produce apparent forward-brightened X-ray halos, especially if the wind is streaming from a solar region slightly off-axis from Earth's perspective. XRISM's imaging system, still early in its operational life, may require further calibration to resolve subtle gradients that currently appear smoother than they actually are. But even the natural explanations still leave the sense that 3I Atlas is more active and more structurally complex than expected for an interstellar comet. Its halo is massive. Hundreds of thousands of kilometers is not trivial. Its spectral balance hints at an environment shaped by unique chemical or energetic processes. Its steadiness, real or averaged, raises questions about the underlying mechanics of its gas release. And above all, the very existence of detectable X-ray emission at this level suggests a degree of interaction with the solar wind that belie the assumption that interstellar objects should be inert, frigid fossils.
The XRISM team itself acknowledged the uncertainties. They emphasized the need for continued calibration, particularly to rule out vignetting or detector sensitivity gradients that might exaggerate or distort diffuse emissions. They stressed that preliminary images are not final interpretations, that the glow could be partially instrumental in origin, and that extended structures in X-ray images must be analyzed with caution. In other words, the mystery is still open, not because something impossible has been found, but because the data sits at the boundary between what we understand and what we are still learning. Yet the emotional weight of observing an object from another star system in X-rays cannot be understated. Comets from our own solar system have well-mapped behaviors, but interstellar comets bring unknown chemical histories, unknown cosmic radiation exposure, unknown internal structures, and unknown thermal responses to sunlight. A halo bias toward carbon and nitrogen could point to a birthplace unlike any region near our sun. A stable emission could reflect a giant slow-releasing reservoir of exotic ices. A forward-facing glow could simply be the solar wind revealing a coma shaped by unfamiliar physics. These possibilities are not only more likely than artificial explanations, they are vastly more interesting in what they imply about planetary systems beyond our own. We are witnessing the early stages of a scientific puzzle that will unfold incrementally as XRISM continues analyzing its data and as other observatories join the hunt. Each new observation of 3I Atlas adds a thread to a tapestry we've never woven before, a map of interstellar chemistry and behavior drawn from the light of a foreign object illuminated in high-energy wavelengths. Whether the glow proves to be unusual chemistry, solar wind geometry, an instrumental illusion, or something still unimagined, highlights how little we know about the material that drifts between the stars and occasionally wanders into our lives as a cosmic messenger. For now, 3I Atlas remains both familiar and alien. Familiar in its comet-like trajectory and faint tail, alien in its spectral fingerprint and massive X-ray halo. Its glow may yet turn out to be entirely natural, a signature of exotic ices forged in a cradle light years away. Or it may reveal processes we have never observed in comets, interstellar or otherwise. The possibility of misunderstanding, of misinterpreting early data remains high, but that is the nature of exploration at the edges of knowledge. What we know for certain is that XRISM has shown us something surprising, something that challenges our assumptions, something that pushes us to ask deeper questions about the nature of interstellar visitors.